Hello again. So, as usual, whenever we learn a new mathematical operation, we need to talk about the properties of that operation. Does it behave like other operations that we are used to, regular multiplication or scalar multiplication of vectors? And so I just want to highlight on page 372 in your textbook, there is a box that goes through the properties of dot product. So you can read through those. Many of them are similar to the properties for vector addition, commutativity. So the order that we do the dot product in doesn't matter. Associativity and distributive property all apply. So you can have a look at those. Those are properties 2, 4, and 5. I just want to highlight properties 1 and 2 because they're going to turn out to be really important. So property 1 we've already seen, and that is that if we have two vectors u and v that are perpendicular, then that implies, and this works in both directions, I'll tell you what that means in a minute, that the dot product of those two vectors will be 0. And so we saw that in the applet, we saw that in an example I did in my last video. So this double-headed arrow here, I just want to make clear what this is about. This double-headed arrow means that it works in both directions. So it means that if we know that u and v are perpendicular vectors, then we also know that their dot product will be 0. And likewise, if we know that their dot product is 0, then we know that the vectors are perpendicular. So it's going to turn out to be a really important property in the application of dot product that we're going to see in the next section. The second vector, this is actually property number 3 that I want to highlight here. Second property I want to highlight is number 3, which is that for any vector u dot u, so a vector dotted with itself, is actually equivalent to the magnitude of that vector squared. So I'm going to verify that using a vector u 1, negative 3, and I've just picked this vector randomly. You can use any vector you like. You can also do it in general, which I believe is one of the examples in the textbook that you can try. I think it's example 5, where you prove that algebraically. So let's just do it with the numerical vector here. So u dot u, remember the definition for dot product for Cartesian vectors, you would multiply the first component by itself and add that to the second component multiplied by itself. And so that comes out to 1 plus 9, which is 10. And then if we do the magnitude of u, you need to recall how to do this from the gizmo and from 7.1. To do the magnitude of vector u in Cartesian form, you would do the square root of the first component squared plus the second component squared, which is the square root of 10. And then the magnitude of u squared just basically gets rid of that square root, and so it's 10. And so we verified with one example at least that the dot product of a vector with itself is equal to the magnitude of the vector squared. Now I just want to go ahead and do one more question here with you. Question 3 on page 376. I'm going to do parts B and C. So 3B and C on page 376 in your textbook. Let's start with 3B. It says use the properties of the dot product to expand and simplify each of the following where k and l are real numbers. So we're given k, so k and l are just scalars. And you know this because you were told in the question, as well as the fact that they don't have vector signs on top of them. Oops. Let me fix that L. It's a little thick. Okay. So we apply our properties of dot product. One of them is distributive property is applicable. And so we'll distribute the LV on the two terms in the first bracket. If it's easier for you, you can move the LV to the front, but it works the same either way. And so KU times LV would be KL. I'm just grouping the scalars, and then times U dot V. We can't just write UV because we can't multiply vectors normally like we would be multiplying scalars. So we have to write U dot V. And then minus L and V dot V. L times V dot V. So let's just see if we can simplify this a little bit. U dot V, we could, no, we can't do much with that, so we'll leave it as U dot V at this point. And then V dot V is equivalent to the magnitude of V squared, according to the property number 3 in the box that we just looked at. Yeah, and so we would leave it like that. Now, I suppose if we knew that K and L were given as geometric vectors, we could go one step further and change U dot V to magnitude of U, magnitude of V, cos theta. So that would be another possibility to leave it like that as well. Not sure what they do in the textbook. Oh, hi guys, I'm back. I paused you because I just wanted to check how they gave the answer to 3B in the textbook. And they actually left it here with the dot product. They didn't bother to go to the next stage. So let's just leave it there. Alright, I just want to look at 3C now. Same page, same question. And so the question for part C is U minus V dot U minus V. Now notice that I make my dot kind of big, so that's to distinguish it from just a regular multiplication dot, because sometimes we use dot for multiplication as well. So make sure it looks like a dot product and not just a multiplication. So here we could apply distributive property again, or a FOIL, since we have a binomial times a binomial. So that would give us U dot U minus U dot V minus V dot U minus V dot V. And then we can simplify this a little bit because U dot U is equal to the magnitude of U squared. U dot V and V dot U, because dot product is commutative, are actually the same thing. And so these are two like terms, so I'm going to collect them. So it's going to be minus 2 U dot V. And then V dot V will also be the magnitude of V squared.